Hey everyone, and welcome to The Explainer. I am absolutely thrilled you're joining us today. We are going to be diving right into the fundamental building blocks of electricity. Now I know this is a topic that can sometimes feel a bit abstract, maybe a little heavily mathematical, but we're going to break it all down. We're going on a highly logical step-by-step journey today. So by the end of our time together, you won't just be memorizing formulas. You're going to truly understand the invisible forces that are literally powering your modern world.
To hook right into this, I want you to picture an incredibly common scenario. What is actually happening inside the walls when you flip a switch? You walk into a dark room, you casually flick a little piece of plastic on the wall, and boom, instantly a light bulb across the room completely lights up. But behind that split-second everyday convenience is this insanely chaotic microscopic world of forces, high-speed collisions, and massive energy transfers. So let's dive right in and uncover the hidden physics behind that simple switch.
All right, here is our roadmap for today's explainer. First up, charge, current, and flow. Then, the push and the pushback. After that, Ohm's law in action, followed by inside the battery. And finally, mastering electrical circuits.
Okay, part 1. Charge, current, and flow. Let's zoom way into the microscopic level.
The sheer scale of what we're talking about here is just mind-boggling. In physics, we measure the quantity of electric charge in a unit called the coulomb. But here's the thing, a single electron carries a remarkably tiny fraction of a charge. So to get just 1 coulomb of negative charge, you need a massive, moving army of exactly 6.25 times 10 to the 18th power electrons. That is literally 6 quintillion 250 quadrillion electrons moving together just to make up one single standard unit of electrical charge. No way, right?
And when that massive army of electrons actually gets moving, that's what we call current. It's super helpful to think of current using the classic water analogy. Current is basically our flow rate. The official measurement for this flow is the ampere, named after the French physicist André Ampère. 1 ampere is simply the continuous flow of 1 coulomb of charge, so all those quintillions of electrons passing through a specific slice of a wire in exactly 1 second. It is literally the volume of the electrical river rushing past you.
Moving right along to part 2, the push and the pushback. Let's talk about the tension in our system.
So if the ampere is our water's flow rate, the volt is our water pressure. It's the absolute crucial push required to force those electrons through the circuit. Because remember, electrons naturally repel each other. They don't want to be crammed together. You have to do actual physical work to move them. The strict textbook definition, 1 volt of potential difference means exactly 1 joule of work is being done to force our 1 coulomb of charge from one point to another, fighting against those repulsive forces the whole way. Without this push, this potential difference, the electrons just kind of vibrate randomly in place. With the push, they march forward. But as they march forward, they experience some serious pushback. Moving electrons don't exactly get an empty, open highway. Inside a metal wire, it is basically an obstacle course. As the free electrons are shoved forward, they are constantly crashing into the massive, fixed positive ions of the metal itself. And every single collision causes the electrons to lose a bit of their kinetic energy, which gets released as heat. It is exactly like friction in a water pipe. The wire physically resists the smooth flow of the current. And we measure this electrical friction, or this obstruction, in ohms. Now, this is absolutely crucial. See how these 3 foundational units perfectly lock together. 1 ohm of resistance is perfectly defined as the exact amount of obstruction that exists if exactly 1 ampere of current flows while 1 volt of potential difference is actively pushing it. So there we have it, the big 3 of electricity: the push, which is volts, the flow, which is amperes, and the pushback, which is ohms.
All right, part 3, Ohm's law in action. Let's see how they mathematically link together.
Way back in 1826, a German scientist named George Simon Ohm discovered the golden rule of electrical circuits. He realized that, assuming the temperature stays constant, the current flowing through a wire is perfectly, directly proportional to the voltage applied across it. This gives us the legendary equation, V equals I times R, or voltage equals current multiplied by resistance. It's wonderfully simple. If you double the push, you exactly double the flow, as long as the friction remains constant.
But, the real world is surprisingly messy, and not all materials play strictly by Mr. Ohm's rules. We really have to draw a sharp distinction here. Ohmic resistors, like your standard copper wires, obey the law perfectly. If you plot their voltage versus current on a graph, you get a beautiful, straight, predictable line. But then we have non-ohmic resistors, like LED lights or glowing bulb filaments. They do not obey the law. As a traditional filament heats up, its positive ions start vibrating intensely, which causes way more collisions, actively changing the resistance on the fly. The graph actually curves. The resistance is dynamic.
And we can actually quantify these inherent material differences. If we look at the specific resistance or resistivity of different materials, notice how incredibly low the number is for copper, just 1.73 times 10 to the negative eighth. It offers very few collisions, which is exactly why we use it to seamlessly transmit power through the walls of our homes. But compare that to an alloy like nichrome. Its resistance is almost 60 times higher, and we rely on that high resistance intentionally. When we force current through nichrome, all those extra collisions generate massive amounts of heat. That is literally how your morning toaster works.
On to part 4, inside the battery. Let's pop the hood on our chemical engine.
Now, there is a very common misconception out there about what a battery promises on the label versus what it actually delivers in reality. Electromotive force, or EMF, which despite the name is totally not a force, is the total available energy per unit charge when the circuit is completely open. Basically, when no current is flowing at all. It's the theoretical maximum push. But terminal voltage is the real-world push you actually measure across the battery terminals once the switch is closed and current is flowing. And the big secret here, the terminal voltage is always less than the EMF.
So, why does the voltage magically drop the second you close the circuit? Well, because even the battery itself fights the flow. A battery gets its power from chemical reactions inside a liquid or paste, which we call an electrolyte. But as the charged ions flow through this internal electrolyte, they face obstruction too. We call this internal resistance, and we usually denote it with a little r. This internal friction literally steals a fraction of the total voltage just to push the current through the battery itself before that energy ever even reaches your device.
And finally, part 5, mastering electrical circuits. Let's put all the pieces together. When we build things in the real world, there are two primary ways to wire up our electrical components. In a series circuit, there is strictly one single continuous path for the electrons. They have to flow from the positive terminal, trudge through every single resistor in a line to get to the negative terminal. But in a parallel circuit, the main path beautifully splits into multiple separate branches. It actually gives the current options on how to get from point A to point B.
These two setups behave completely differently. In a series circuit, because there is literally only one path to take, the exact same amount of current is stubbornly forced through every single component. But the total push, the potential difference from the battery, has to be divided up to get the charge through each consecutive obstacle. Because you're chaining these obstacles one right after another, the total equivalent resistance just stacks up heavily. It really slows down the overall flow of the entire system.
But a parallel circuit? It offers some fascinating, completely counterintuitive magic. Because each branch connects directly back to the main power lines, every single resistor gets the exact same total potential difference. They all feel the full push of the battery. The current, however, divides up among the different branches. And here is the truly amazing part. By providing more parallel pathways for the current to take, you actually lower the overall total resistance of the circuit. Think of it like opening up extra lanes on a crowded highway. The total flow of traffic just skyrockets.
So, throughout this explainer, we've seen how friction and resistance dictate the absolute rules of electricity, constantly generating heat and losing energy. Interestingly, the source text briefly touches on superconductors, materials like mercury or niobium, that, incredibly, can drop to absolutely zero resistance, no friction, infinite conductance, completely zero lost energy. It's basically the holy grail of physics. But, as the source notes, they currently only achieve this at incredibly cold temperatures, hovering right near absolute zero. So I want to leave you with this to ponder. If zero-resistance superconductors could flawlessly transmit power across the globe and shrink our computers down to the size of a coin, what incredible breakthroughs are needed to make room-temperature superconductors a reality? And how will it completely change our world when we finally figure it out? Thank you so much for joining me today. Keep learning and stay curious.